Everything you know about the speed of light is wrong. 300,000 kilometers per second sounds fast until you realize what it actually means. We are trapped, forever locked behind a barrier that makes the universe unreachable. Let me show you why the fastest thing in the universe is too slow. And here is a question. If you could travel at the speed of light without the side effects, where would you go first? Let us know in the comments. I will pin the most creative answer. Now let's begin. Our fastest spacecraft, Voyager 1, has been screaming away from Earth at about 60,000 kilometers per hour. That's incredibly fast by any human standard. If you could travel at that speed, you'd circle our entire planet in less than 40 minutes. Voyager has traveled farther than any human-made object in history, over 25 billion kilometers from home. It crossed into interstellar space in August of 2012, becoming the first spacecraft to leave our sun's protective bubble and enter the space between stars. Impressive, right? Here's the gut punch. Despite traveling for almost 50 years at that extraordinary speed, Voyager 1 still hasn't traveled even one light day from Earth. That's the distance light covers in a single day. Light makes that journey in 24 hours. Voyager 1, our fastest ambassador to the stars, has taken nearly half a century and still hasn't gotten there. According to NASA and the Jet Propulsion Laboratory, Voyager 1 is expected to reach one light day distance in November of 2026. Almost 50 years to travel what light does in a single rotation of our planet. Let that sink in. Light is supposed to be fast, the universal speed limit. Yet even light, moving at nearly 300,000 kilometers every single second, takes a full day to cover the distance Voyager has barely reached after decades of travel. And we're still talking about our cosmic backyard. We haven't even left our immediate neighborhood yet. Now let's zoom out a bit. The nearest star to our Sun is Proxima Centauri, sitting approximately 4.2 light-years away. That means light from that star takes 4 years and 2.5 months to reach your eyes. When you look at Proxima Centauri, you're seeing it as it was when you were 4 years younger. Maybe you were in a different school, had different friends, lived in a different place. That star's light has been traveling through the empty void of space all that time just to reach your retina tonight. But here's where it gets unsettling. If we wanted to send Voyager 1 to Proxima Centauri at its current speed, it would take over 73,000 years to arrive. 73,000 years. Humans didn't even have written language 73,000 years ago. Our entire recorded history, every empire, every invention, every war, every discovery spans only about 5,000 years. Voyager would need more than 14 times that long to reach our nearest neighbor. And we're talking about a star system that's only 4 light-years away. Only 4 years for light. More than 70 millennia for us. If you're enjoying this mind-bending journey through space and time, hit that subscribe button and give this video a thumbs up. Sharing this knowledge and exploring the universe together is what this channel is all about, and your support helps me bring more of these cosmic stories to you. Now let me take you even farther out, because 4 light-years is still just a tiny step. Our Milky Way galaxy, the cosmic island we call home, stretches approximately 100,000 light-years from edge to edge. Imagine that. If you could somehow travel at light speed starting from one side of our galaxy, it would take you 100,000 years to reach the other side, and you'd be moving at the fastest speed physically possible in our universe. The center of our galaxy, where a supermassive black hole named Sagittarius A star sits waiting, is about 27,000 light-years from Earth. The light you'd see from that region tonight left that place 27,000 years ago. Humans were still in the Stone Age. We were painting on cave walls and hunting woolly mammoths. The light that left the galactic core back then is only just now arriving at Earth, bringing us images of a past so distant it predates all of civilization. Here's what makes this truly terrifying in the most awe-inspiring way. We can never see the galaxy as it is right now. We can only see its past. Every photograph, every observation, every beautiful image of our galaxy is ancient history. The stars you see might have already died. The nebulae might have already collapsed or expanded. We're cosmically blind to the present, forever watching reruns of a universe that no longer exists in the form we observe. But let's push even further, because our galaxy is just one of potentially 2 trillion galaxies in the observable universe. The Andromeda galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. When you look at Andromeda through a telescope, you're witnessing light that began its journey 2.5 million years ago. Back then, early human ancestors were just learning to use stone tools. We hadn't even evolved into modern Homo sapiens yet. That ancient light has been crossing the void ever since, finally reaching us tonight. And Andromeda is close, cosmically speaking. It's practically next door. The James Webb Space Telescope, humanity's most powerful eye on the universe, has peered even deeper into space and time. In December of 2025, astronomers using Webb confirmed the second and fourth most distant galaxies ever observed. These galaxies exist in a region called Pandora's Cluster, and they're located approximately 33 billion light-years away from us. Yes, you heard that correctly. 33 billion light-years. Now you might be thinking, wait, didn't you say the universe is only about 13.8 billion years old? How can something be 33 billion light-years away? Excellent question, and this is where things get even more mind-bending. The universe has been expanding since the Big Bang. Those galaxies were much closer when they emitted the light we're seeing now, but as that light traveled toward us, space itself stretched, carrying those galaxies farther and farther away. So while the light has been traveling for about 13.3 billion years, the galaxies themselves are now 33 billion light-years distant due to cosmic expansion. Think about what this means. We're observing these galaxies as they appeared when the universe was only around 730 million years old, just 5% of its current age. We're literally watching the universe's childhood. The light from those galaxies has been racing toward Earth since before our sun existed, before our solar system formed, before anything remotely resembling our cosmic neighborhood came into being. That light predates Earth itself by billions of years. These aren't just red dots in space either. According to research published in 2023, these distant galaxies appear surprisingly large and structured, with one resembling a peanut shape and another looking fluffy and diffuse. They're showing us that even in the universe's infancy, galaxies were already forming complex structures. This challenges some of our theories about how quickly galaxies could grow in the early cosmos. In March of 2025, Webb made another groundbreaking discovery. Astronomers observed the most distant supernova ever detected. This stellar explosion, designated SN in GRB 250314A, occurred during the epoch of reionization, when the first stars and galaxies were beginning to light up the dark universe. The explosion happened when the universe was only about 730 million years old. Here's what's fascinating. This ancient supernova was first detected as a gamma-ray burst, one of the most energetic events in the universe. The burst was caught by the space-based multiband astronomical variable objects monitor called SVOM, and then Webb followed up with detailed observations. What surprised astronomers was that despite happening in the universe's childhood, this supernova closely resembles gamma-ray burst supernovae in the modern universe. Massive stars were already living and dying in spectacular fashion, following patterns we recognize today. over 13 billion years ago. The light from that explosion has been traveling through space for more than 93% of the universe's entire existence. It passed through expanding space, navigated around galaxies and dark matter, threaded through clusters and voids, all to reach our telescopes in 2025. And it moved at the speed of light the entire time, never slowing, never stopping, yet still taking billions of years to complete its journey. This is the terrifying truth about light speed. It's simultaneously the fastest thing in the universe and agonizingly slow when measured against cosmic distances. Nothing can move faster, yet light itself is a cosmic snail when you zoom out to universal scales. Actually, speaking of traveling these immense distances, if you're wondering how humanity might ever hope to cross interstellar space and reach even our nearest stellar neighbors, I created an entire video exploring that exact question. How long until humans achieve interstellar travel? I dive deep into the technologies we're developing, the physics we need to overcome, and realistic timelines for when we might actually send humans to another star system. It's a perfect companion to what we're discussing here, so check it out after this video. The link is in the description and on the card above. Now let's talk about what this slowness means for our understanding of the universe. Every telescope is a time machine. When astronomers point Webb or Hubble or any other telescope at the sky, they're not studying the universe as it exists now, they're studying history. The farther we look, the further back in time we see. Webb orbits the Sun at the second Lagrange point, about 1.5 million kilometers from Earth. That's roughly 5 light seconds away. When Mission Control at the Space Telescope Science Institute sends a command to Webb, that signal travels at light speed and takes approximately 5 seconds to arrive. Webb's response takes another 5 seconds to return. Every interaction with this incredible instrument happens on a 10-second delay. Even at light speed, even at distances we consider relatively close in astronomical terms, there's always a lag, always a wait. The planets in our solar system exist on these delays too. Mars ranges from about 3 light minutes to 22 light minutes away, depending on where Earth and Mars are in their orbits. When we send rovers to Mars, every command we transmit takes several minutes to arrive, and every response takes several minutes to return. Imagine driving a car where your steering wheel inputs take up to 22 minutes to reach the wheels. That's the challenge of exploring even our neighboring planet. Neptune, the most distant planet in our solar system, sits about 4 light hours away. Messages to a probe near Neptune take 4 hours to arrive. If something goes wrong, we won't know for 4 hours, and any fix we send takes another 4 hours to reach the spacecraft. By the time we've completed a single back-and-forth communication, 8 hours have passed. An entire workday spent sending a single question and receiving a single answer. This communication delay becomes a prison when we think about exploring beyond our solar system. If we sent astronauts to Proxima Centauri, every message they sent home would take 4.2 years to reach Earth. Every reply from Earth would take another 4.2 years to reach them. A simple conversation would span 8.5 years. You could ask someone how they're doing, and by the time you received their answer, nearly a decade would have passed. They might not even be alive anymore, yet their message would just be arriving. This is what I mean when I say the speed of light is terrifyingly slow. It isolates us. It traps us in our tiny corner of space. Even if we could build ships that traveled at 99% of light speed, which is far beyond anything we can currently achieve, crossing our own galaxy would still take over 100,000 years. Reaching Andromeda would require 2.5 million years. The universe is so vast that even at the cosmic speed limit, you'd need millions of years to visit our closest galactic neighbors. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends about 46.5 billion light-years in every direction. That's a diameter of 93 billion light-years. If you wanted to cross the observable universe at light speed, you'd need 93 billion years, but the universe is only 13.8 billion years old. The universe itself isn't old enough for light to have crossed from one side of the observable universe to the other and back again. Let that concept settle in your mind. The universe is so large that light, traveling since the moment of the Big Bang, hasn't had time to traverse it. There are regions of space that are forever beyond our view, not because they don't exist, but because their light hasn't had enough time to reach us yet. And due to the acceleration of cosmic expansion, there are regions of space whose light will never reach us, no matter how long we wait. The universe is expanding faster than light can cross it. Dark energy, the mysterious force driving this acceleration, is pushing distant galaxies away from us at speeds that exceed the speed of light. Now, before you say, "Wait, I thought nothing could move faster than light," let me clarify, nothing can move through space faster than light. But space itself can expand at any rate. These distant galaxies aren't moving through space faster than light. Rather, the space between us and them is stretching so rapidly that the distance grows faster than light can traverse it. This means there are galaxies we can see now whose light will eventually redshift into invisibility. In trillions of years, if any astronomers exist in our galaxy, they'll look out at the universe and see almost nothing beyond our local group of galaxies. Everything else will have been carried beyond the cosmic horizon by expansion. Future astronomers will look at an apparently empty universe, unaware that billions of galaxies once filled the sky, because the light from those galaxies can no longer reach them. We live in a special epoch, a golden age of astronomy, where we can still observe the distant universe before expansion hides it from view forever. We're lucky, in a cosmic sense, to exist at a time when the universe is old enough to have formed complex structures, but young enough that we can still observe much of it. But let's bring this back to something more immediate, something that might hit closer to home. Every time you look at a star, you're seeing ancient light. Betelgeuse, the bright red star in the constellation Orion, sits about 550 light-years away. When you see Betelgeuse tonight, you're looking at light that left that star in the late 1400s. Columbus hadn't yet sailed to the Americas. The Renaissance was just beginning in Europe. That star could have exploded in a brilliant supernova 200 years ago, and we wouldn't know yet. The explosion's light would still be making its way across the void, and it might arrive tomorrow, next year, or 2 centuries from now. We wouldn't get any warning. One night you'd go outside, look up, and suddenly there would be a new star in the sky, bright enough to see during the day, casting shadows at night. Ancient astronomers would have thought it was a sign from the gods. We would know it's a supernova, but we'd be watching an event that happened half a millennium ago, a cosmic recording arriving at our eyes long after the explosion finished. Every photon of light that enters your eye has a story. That photon might have been created in the core of the sun through nuclear fusion, then spent 170,000 years bouncing around inside the sun's dense interior before finally reaching the surface. From there, it traveled 8.3 minutes through space, passed through Earth's atmosphere, and landed on your retina. That single photon began its journey before modern humans even evolved, and it ended that journey in your eye a fraction of a second ago. The light from the Andromeda galaxy that you see tonight was emitted 2.5 million years ago. Our ancient ancestors, Australopithecus afarensis, were walking upright in Africa. That photon has been traveling through the emptiness of intergalactic space ever since, covering 2.5 million light-years, or about 23 billion trillion kilometers. It survived that entire journey, navigating through the darkness, avoiding absorption by dust clouds and gas, bending slightly around massive objects due to gravitational lensing, all to arrive at this exact moment and enter your eye. And here's something beautiful. You might be the only being in the universe that photon will ever touch. It traveled for 2.5 million years, crossing an incomprehensible void, and its journey ended with you. In a very real sense, you're connected to Andromeda by that photon. You've caught a messenger from another galaxy, and that messenger is showing you the past. This is what I mean when I say we're made of stardust and connected to the cosmos. These aren't just poetic words. They're literal truth. The atoms in your body were forged in the hearts of stars that exploded billions of years ago. The light entering your eyes right now has traveled for years, decades, millennia, or even billions of years to reach you. You are part of this vast cosmic web, touching deep time with every glance at the night sky. But the slowness of light also reveals something profound about causality and the structure of the universe itself. Because light speed is finite, because information cannot travel faster than light, the universe has a built-in delay mechanism. Events that happen far away take time to affect us. This isn't just a quirk, it's fundamental to how reality works. Einstein's special relativity showed us that the speed of light isn't just a speed limit for motion, it's the speed limit for causality itself, for cause and effect. Nothing can influence anything else faster than light can travel between them. This means that the universe has a structure, a fabric of causality, where events are connected by light cones. Your present moment can only be affected by events in your past light cone, the region of space-time from which light could have reached you. Similarly, you can only affect events in your future light cone, the region of space-time that light from your current position can reach. Everything outside those cones is causally disconnected from you. It might as well not exist because it cannot affect you and you cannot affect it. The finite speed of light creates islands of causality in space-time, separating events that can influence each other from those that cannot. This has profound implications. When we observe a supernova exploding 10,000 light-years away, that explosion happened 10,000 years ago in our reference frame, but we couldn't have known about it until now. For those 10,000 years, that supernova was outside our past light cone. It existed, it exploded, it sent out shockwaves and created new elements, but none of that could affect us until the light reached us. Now imagine this on a cosmic scale. There are events happening right now at this very moment in distant galaxies that we won't witness for millions or billions of years. Stars are being born, planets are forming, perhaps civilizations are rising and falling, black holes are colliding, galaxies are merging. All of this is happening in the universe's present moment, but we're locked out of knowing about it because the light carrying that information hasn't reached us yet. Conversely, any alien civilization looking at Earth from 1,000 light-years away would see Earth as it was in the year 1026. They'd observe a medieval world with no cities of light, no radio signals, no evidence of advanced technology. If they had powerful enough telescopes, they might see smoke from cooking fires, the Great Wall of China, perhaps sailing ships on the oceans, but they wouldn't see modern civilization because that light hasn't reached them yet. If those aliens are looking at us right now, they're seeing our past. If we're looking at them right now, we're seeing their past. Neither of us can see each other as we truly are in this present moment. We're forever separated by the crawling pace of light across cosmic distances. This creates a strange paradox when you think about it. What does now even mean on a cosmic scale? There's no universal present moment. There's no cosmic clock ticking away that synchronizes the entire universe. Instead, now is relative, dependent on your position and motion through space-time. Your now and the now of someone in the Andromeda galaxy are different slices through the fabric of space-time. Einstein's relativity tells us that simultaneity, the concept of things happening at the same time, breaks down across cosmic distances. Two events that appear simultaneous from one reference frame might not be simultaneous from another reference frame, moving at a different velocity. Time itself is woven into the fabric of space, creating space-time, and observers in different states of motion experience time differently. This isn't science fiction, it's been proven through countless experiments. Atomic clocks on airplanes tick at different rates than identical clocks on the ground. GPS satellites have to account for relativistic time dilation, or their positioning data would be off by kilometers. Astronauts on the International Space Station age slightly slower than people on Earth's surface. Time is not absolute. It bends, stretches, and flows at different rates depending on gravity and velocity. The speed of light sits at the heart of all this. It's not just a speed, it's a fundamental constant that weaves together space, time, energy, and matter into a unified framework. The equation E equals mc squared, perhaps the most famous equation in physics, shows that energy and mass are equivalent, related by the speed of light squared. That speed, represented by the letter c, is so fundamental that it appears in equations describing everything from quantum mechanics to black holes to the expansion of the universe itself. But despite its fundamental importance, despite being the cosmic speed limit, light is still maddeningly slow when measured against the scale of the universe. This slowness shapes everything about how we explore and understand the cosmos. Consider the Hubble Space Telescope, which orbits Earth at an altitude of about 540 kilometers. Light from Hubble takes only about 1.8 milliseconds to reach Earth. Communication is essentially instantaneous from a human perspective. We can control Hubble in near real time, adjusting its instruments and downloading images without significant delay. The James Webb Space Telescope, positioned at the second Lagrange point, sits about 1.5 million kilometers away. That 5-second light travel time creates a noticeable delay, but still allows for relatively responsive control. Engineers can send commands, wait 10 seconds for a round-trip confirmation, and continue working. It's manageable, but now imagine a telescope positioned at the edge of our solar system, perhaps near the heliopause where Voyager 1 crossed into interstellar space. That's about 18 light hours away. Commands would take 18 hours to arrive, and confirmations would take another 18 hours to return. You'd send an instruction in the morning, and if everything worked perfectly, you might receive confirmation the following afternoon. If something went wrong, you wouldn't know for 36 hours, and any fix you attempted would take another 36 hours to implement. That's 3 full days for a single command cycle. Now think about a mission to another star. Even our nearest stellar neighbor, Proxima Centauri, is 4.2 light-years distant. A probe sent there couldn't be controlled from Earth in any meaningful way. The communication delay would be over 8 years for a single back-and-forth exchange. The probe would have to be completely autonomous, making its own decisions, carrying out its mission without any possibility of real-time guidance from home. By the time Mission Control learned about a problem and sent a solution, the probe might have already failed or solved the issue on its own. This is why interstellar exploration presents such monumental challenges. It's not just about building a fast enough spacecraft, although that's incredibly difficult. It's also about creating machines intelligent enough to function independently for decades or centuries, resilient enough to survive the hostile environment of interstellar space, and sophisticated enough to make scientific discoveries without human guidance. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973 respectively, carry plaques designed to tell any alien civilization that might find them where the probes came from. These plaques show the position of our Sun relative to nearby pulsars, depict human figures, and include other information about Earth. But here's the sobering reality: those spacecraft are traveling so slowly relative to cosmic distances that they won't reach another star system for millions of years. The chances of them ever being found are vanishingly small, and even if they were discovered, the civilization that created them, our civilization, might be long extinct by then. Voyager 1 and 2 carry golden records, phonograph discs containing sounds and images from Earth, meant to communicate the story of our world to any extraterrestrial intelligence that might encounter them. Carl Sagan, who chaired the committee that selected the contents, called them messages in a bottle cast into the cosmic ocean. But that ocean is so vast, and our bottles are moving so slowly, that they might drift for billions of years without ever reaching a shore. These missions represent humanity's first attempts to reach beyond our solar system, and they revealed the brutal truth about cosmic distances. We've sent our fastest spacecraft toward the stars, and they're moving at a pace that makes geological processes look rapid by comparison. Continental drift, the movement of Earth's tectonic plates, occurs at a few centimeters per year. At that rate, over the 73,000 years it would take Voyager to reach Proxima Centauri, the continents on Earth would shift by several kilometers. The world Voyager left behind would be geographically different by the time it arrived at another star. Let's talk about what all of this means for the possibility of contact with extraterrestrial civilizations. The Fermi paradox asks a simple but profound question. If the universe is so vast, so ancient, and filled with billions of galaxies, each containing billions of stars, many with planetary systems, why haven't we detected any signs of alien civilizations? Where is everybody? The slowness of light might be part of the answer. Even if technologically advanced civilizations exist elsewhere in our galaxy, the vast distances and the speed limit imposed by light create enormous barriers to contact. A civilization 1,000 light-years away could be broadcasting radio signals right now, powerful beacons announcing their presence to the cosmos, but those signals won't reach Earth for another 1,000 years. Meanwhile, our radio signals, which have only been leaking into space for about a century, have created a bubble of detectability only 100 light-years in radius. That bubble contains roughly 14,000 stars. In a galaxy of 200 to 400 billion stars, we've announced our presence to a tiny fraction of our cosmic neighborhood, and any response from a civilization at the edge of that bubble would take 200 years to arrive, 100 years for our signal to reach them, and another 100 for their reply to reach us. If we detected an alien signal tomorrow from a source 500 light-years away, we'd be hearing a message sent in the 1500s. We could send a reply, but it wouldn't arrive until the 2600s. Their response to our response wouldn't reach Earth until the 3100s, more than a millennium from now. A simple conversation would span over 1,000 years. Entire civilizations could rise and fall in the time it takes to exchange a few sentences. This might explain part of the Great Silence. Even if the galaxy is teeming with intelligent life, the speed of light creates insurmountable barriers to real-time communication across interstellar distances. Civilizations might be having conversations right now, but those conversations unfold over timescales of centuries or millennia. By the time a message crosses space, the civilization that sent it might have evolved beyond recognition, might have gone extinct, or might have lost interest in the conversation entirely. Some scientists have proposed that advanced civilizations might use techniques we haven't discovered yet to circumvent the light speed barrier. Hypothetical concepts like wormholes, warp drives, or quantum entanglement communication appear in theoretical physics, but all of them face enormous obstacles that might be insurmountable. Wormholes, tunnels through space-time that could connect distant points, emerge from Einstein's equations as mathematical possibilities. But creating a traversable wormhole would require exotic matter with negative energy density, something we've never observed and that might not exist. Even if it does exist, the amount needed to stabilize a wormhole large enough for a spacecraft might exceed the total mass energy of entire star systems. We're talking about civilizations that could manipulate the fabric of space-time itself, that could harness energies that dwarf anything we can currently imagine. Warp drives, popularized by science fiction but grounded in serious theoretical work by physicists like Miguel Alcubierre, would involve contracting space-time in front of a spacecraft and expanding it behind, allowing the ship to effectively move faster than light without actually violating relativity. The spacecraft wouldn't move through space faster than light. Instead, it would surf a wave of compressed and expanded space-time. But again, this requires exotic matter, enormous energies, and physics we don't fully understand. Current estimates suggest you'd need more energy than exists in multiple stars to create a warp bubble, and even then, there might be fundamental physical laws that prevent it from working. Quantum entanglement, the phenomenon where two particles remain connected such that measuring one instantly affects the other regardless of distance, seems like it might offer a way to send information faster than light. Einstein famously called this spooky action at a distance and was deeply uncomfortable with it. But here's the catch. While entanglement creates correlations between particles instantly across any distance, you can't use it to transmit information. When you measure one particle, you get a random result, and the entangled particle gives a correlated random result. There's no way to encode a message in that randomness that the other party can decode without comparing results through conventional, slower-than-light communication channels. Every attempt we've conceived to bypass the light speed limit runs into either practical impossibilities or fundamental physical constraints. The universe seems designed, in a sense, to enforce the speed of light as an absolute barrier. And maybe that's for the best. If faster-than-light travel or communication were easy, the universe might be a much more dangerous place. Hostile civilizations could reach across vast distances to harm others. The cosmic speed limit acts as a quarantine mechanism, ensuring that each civilization has time to mature in isolation before potentially encountering others. But let's return to what we can observe, to the science we can actually do with light, moving at its frustratingly slow, yet fundamentally constant pace. Astronomers have developed ingenious techniques to extract information from ancient light, to read the stories written in photons that have traveled for billions of years. Spectroscopy, the study of how light interacts with matter, allows us to determine what distant objects are made of. Every element absorbs and emits light at specific wavelengths, creating unique patterns like fingerprints. When we spread the light from a distant star into a spectrum, we can identify which elements are present in that star's atmosphere by looking for those fingerprints. We've used this technique to determine the composition of stars thousands of light years away, analyzing ancient light to understand the chemical makeup of objects we'll never physically touch. The cosmic microwave background radiation, the afterglow of the Big Bang itself, fills the universe with faint light that has been traveling for 13.8 billion years. This light was emitted when the universe was only 380,000 years old, when it cooled enough for atoms to form and light to travel freely for the first time. That ancient radiation has been stretched by cosmic expansion into microwave wavelengths, and it bathes us from all directions, a relic of the universe's birth. By studying tiny variations in this cosmic background radiation, astronomers have mapped the structure of the infant universe. They've measured its age, composition, and geometry with remarkable precision. They've seen the seeds of galaxy formation, the tiny density fluctuations that would grow over billions of years into the cosmic web of galaxies we see today. All of this from studying light that began its journey when the universe was a hot, dense soup of particles long before stars, planets, or galaxies existed. When we observe distant galaxies, we're not just seeing them as they were in the past, we're also seeing them affected by the expansion of the universe. Light from these galaxies is redshifted, stretched to longer wavelengths because the space through which it traveled was expanding. The farther away a galaxy is, the more its light is redshifted, and by measuring that redshift, we can determine not just the galaxy's distance, but also how fast the universe was expanding when that light was emitted. This is how Edwin Hubble discovered that the universe is expanding in the first place. In 1929, he observed that distant galaxies showed greater redshifts than nearby ones, and he realized this meant they were receding faster. The universe wasn't static, it was growing, and it had been growing for billions of years. This single observation, possible only because light preserves information about its journey across cosmic distances, revolutionized our understanding of the cosmos. The expansion itself creates another aspect of light's terrifying slowness. As the universe expands, the distances between galaxies grow, and light traveling between them has to cross an ever-increasing gap. A photon emitted from a distant galaxy 13 billion years ago has been fighting against cosmic expansion for its entire journey. Space has been stretching beneath it, pulling its destination farther away, even as it races toward us at the speed of light. That photon has been running a race where the finish line keeps moving backward. In fact, for the most distant galaxies we can observe, the ones whose light was emitted when the universe was very young, the expansion of space during the light's journey has stretched the distance the photon had to travel far beyond what the distance was when it started. A galaxy that was perhaps 30 million light-years away when it emitted the light we're seeing now is actually over 30 billion light-years away by the time that light reaches us, because space expanded dramatically during the photon's journey. This means that light from the most distant objects has been traveling for over 93% of the universe's history, crossing an ever-expanding ocean of space just to reach our telescopes. And yet, despite traveling at the cosmic speed limit for 13+ billion years, these photons still took that long to arrive. Imagine running at maximum speed for your entire life and still not reaching your destination. That's what light experiences when crossing cosmic distances. The slow cosmic crawl of light also affects our ability to study transient events, things that change or happen quickly on astronomical timescales. Supernovae, for instance, brighten and fade over weeks or months. If a supernova occurs in a galaxy 100 million light-years away, we see it explode 100 million years after it actually happened. But more importantly, we only get one chance to observe it. By the time we detect the explosion, point our best telescopes at it, and begin detailed observations, the event might already be fading. The light showing us the supernova at its peak might have already passed Earth before we even knew to look for it. In 2023, astronomers discovered an incredibly luminous supernova designated SN 2023 YEFX. This explosion, located over 1 billion light-years away, became one of the brightest supernovae ever observed. But by the time it was detected, classified, and studied in detail, it had already begun to fade. Scientists had to piece together what happened during the explosion's peak by analyzing the light that arrived after the brightest moments had passed, like trying to understand a symphony by only hearing the final notes. Gravitational wave astronomy has opened a new window on the universe, allowing us to detect ripples in space-time caused by massive cosmic events like colliding black holes or neutron stars. These waves also travel at the speed of light, and they carry information about cataclysmic events occurring millions or billions of light-years away. On August 17, 2017, The LIGO and Virgo detectors observed gravitational waves from two neutron stars colliding in a galaxy 130 million light-years away. This event, designated GW170817, was the first time humanity detected both gravitational waves and light from the same cosmic event. The collision happened 130 million years ago when dinosaurs still roamed the Earth. Gravitational waves and light traveled together through space for 130 million years, finally reaching our planet on that day in 2017. For all of human history, that collision was in our past, but we couldn't know about it because the information was still in transit. It existed in the universe's timeline, but outside our past light cone, unreachable until the speed of light allowed the signals to finally arrive. This multi-messenger astronomy, combining gravitational waves, light, and other signals, promises to revolutionize our understanding of the universe. But it's still constrained by the speed of these signals. Everything we observe is history. Everything we detect happened in the past, sometimes the distant past, and we're forever locked into observing the universe as it was, not as it is. Now let's consider something even more mind-bending, the concept of look-back time. When you observe an object at a certain distance, you're seeing it as it existed a certain time ago. For nearby objects, this distinction doesn't matter much. The moon as you see it is only 1.3 seconds in the past. The sun as you see it is 8.3 minutes in the past. These delays are negligible for most purposes. But when you look at the Andromeda galaxy, you're seeing it as it existed 2.5 million years ago. When you observe a galaxy 10 billion light-years away, you're seeing it as it existed 10 billion years ago when the universe was less than 4 billion years old. The farther you look, the further back in time you see, until you reach the cosmic microwave background, which shows us the universe at only 380,000 years old. This creates a strange situation. We can map the history of the universe by looking in different directions and at different distances. A galaxy 1 billion light-years to our north shows us the universe 1 billion years ago. A galaxy 2 billion light-years to our south shows us the universe 2 billion years ago. Every direction we look, every distance we probe, we're sampling different epochs of cosmic history. Imagine if you could do this on Earth. Imagine if looking toward the north showed you your city as it was 1 year ago, looking east showed it as it was 10 years ago, looking south showed it as it was a century ago, and looking west showed it as it was a millennium ago. You could stand in one place and observe different time periods simultaneously just by turning your head. That's exactly what astronomers do when they survey the sky at different distances. They're creating a time machine out of telescopes and the finite speed of light. The James Webb Space Telescope was designed specifically to exploit this time machine property. By observing extremely distant and therefore extremely ancient galaxies, Webb allows us to witness the universe's first billion years, the epoch when the first stars and galaxies formed. These observations are showing us things that challenge our theories. In February 2023, astronomers using Webb reported discovering galaxies that appear surprisingly massive and well-developed, despite existing only a few 100 million years after the Big Bang. These galaxies seem to contain more stars than our models predicted could have formed so quickly. Some astronomers wondered if we needed to revise our understanding of galaxy formation, star formation rates, or even the age of the universe itself. Further observations have helped clarify the picture. Many of these galaxies turned out to be less massive than initial estimates suggested, and their unusual brightness could be explained by intense bursts of star formation or the presence of supermassive black holes actively feeding and shining brightly. But the discoveries still push the boundaries of our models, showing us that the early universe was more complex and dynamic than we previously thought. All of these discoveries are possible only because light preserves a record of its journey. Every photon carries information about when and where it was created, what it has traveled through, and how space itself has changed during its voyage. Light is simultaneously a messenger and a time capsule, delivering news from across the cosmos along with proof of when that news originated. But here's another unsettling consequence of light's finite speed. Everything you see, everything you've ever seen, is already gone by the time you perceive it. The person sitting across from you appears as they were nanoseconds ago. Light reflected from their face takes a few nanoseconds to reach your eyes. For practical purposes, this delay is meaningless. You're seeing them essentially as they are right now, but extend this principle. The mountain you see on the horizon appears as it was microseconds ago. The moon appears as it was 1.3 seconds ago. If someone on the moon turned on a powerful laser pointed at Earth, you wouldn't see the light until 1.3 seconds after they switched it on. If that person suddenly died, you'd still see them alive for another 1.3 seconds, observing a living person who was already dead, watching light from a past that no longer exists. This becomes more profound with cosmic distances. Every star you see in the night sky might already be dead. Betelgeuse, which could explode as a supernova at any time, might have already exploded 500 years ago, and we simply haven't received the light from that explosion yet. When you look at the Andromeda galaxy, you're admiring a structure that has evolved and changed over the 2.5 million years its light took to reach you. Stars have been born and died there. Planets have formed. Supernovae have exploded. None of those changes are visible to you because their light hasn't arrived yet. You're seeing a galaxy that, in a very real sense, no longer exists in the form you're observing. The universe you observe around you is a patchwork of different time periods stitched together by the varying distances to different objects. You exist in your present moment, but everything else you see exists in its own past moment, with that past being more ancient the farther away you look. You're standing at the center of a sphere of space and time where every distance corresponds to a different era. This has profound philosophical implications. Is there a real universe that exists right now with all galaxies in their current states simultaneously? Or is the only universe we can talk about meaningfully the one we observe, the patchwork of different times we perceive through light? If something exists but is forever outside our past light cone, beyond the cosmic horizon, impossible to detect or observe even in principle, does it meaningfully exist for us? These questions blur the line between physics and philosophy, between what is measurable and what is metaphysical. But they arise directly from the simple fact that light travels at a finite speed, creating a lag between events and our observation of them. Let's shift to something more concrete: how the speed of light limits our ability to study exoplanets, planets orbiting other stars. The nearest known exoplanet, Proxima Centauri b, orbits the star Proxima Centauri at a distance of 4.2 light-years. This planet was discovered in 2016 through the radial velocity method, which detects the tiny wobble in a star's motion caused by an orbiting planet's gravitational pull. We've learned that Proxima Centauri b is roughly Earth mass and orbits within its star's habitable zone, the region where liquid water could exist on a planet's surface. This makes it one of the most intriguing exoplanets for astrobiology, for the search for life beyond Earth. But here's the frustrating reality. Everything we know about this planet describes how it was 4.2 years ago. The light and radio signals we detect were emitted 4.2 years in the past. If life exists on Proxima Centauri b, if that life has developed technology and is broadcasting radio signals into space right now, we won't detect those signals for another 4.2 years. If that civilization suddenly went extinct yesterday, we won't learn about it until the year 2031. The speed of light creates an unbridgeable information gap between us and our nearest planetary neighbor. Most known exoplanets are much farther away. Kepler 452b, an Earth-sized planet in its star's habitable zone, is 1,400 light-years distant. When we observe this planet, we're seeing it as it existed in the year 626 of the Common Era, when the Byzantine Empire was at its height and the Mayan civilization was flourishing in Central America. The planet has experienced 1,400 years of history since the light we're currently detecting left its vicinity. We have absolutely no way of knowing what has happened there in all that time. If Kepler 452b harbors intelligent life that developed radio technology in the year 1000, they would have been broadcasting for over 1,000 years by now, but their signals, traveling at light speed, would still be 400 years away from Earth. We wouldn't detect them until around the year 2400. Meanwhile, if they're observing Earth with powerful telescopes right now, they're seeing our planet as it was in the year 626, seeing a world without modern civilization, without electric lights, without any evidence of the technological society that exists here now. These time lags create a strange dynamic for the search for extraterrestrial intelligence. The SETI project, the search for extraterrestrial intelligence, scans the sky for artificial radio signals that might indicate the presence of alien civilizations. But any signal we detect would necessarily come from the past, perhaps the distant past. A signal from a civilization 10,000 light-years away would tell us that life existed there 10,000 years ago. That civilization might still exist, or it might have destroyed itself, evolved beyond recognition, or been wiped out by a cosmic catastrophe millennia ago. We'd have no way of knowing until we sent a signal and waited 20,000 years for a response. This makes the search for extraterrestrial intelligence an exercise in patience on timescales that dwarf human lifetimes or even human civilizations. If we detected a signal tomorrow from a source 5,000 light-years away and immediately sent a response, that exchange would take 10,000 years to complete. The scientists who detected the original signal would be dead for millennia before the reply arrived. The civilization that sent the reply might not even remember sending it by the time our response reached them. Carl Sagan explored these ideas in his novel Contact, where scientists detect a signal from Vega, a star 25 light-years away. The signal contains instructions for building a machine, a device that might enable faster-than-light travel or communication. But even in this optimistic scenario, the aliens who sent the message did so 25 years before it was received, and any response would take another 25 years to reach them. That's a 50-year round trip for a simple exchange, and Vega is one of our relatively close neighbors. The speed of light doesn't just limit our communication with potential alien civilizations, it also constrains our ability to explore our own solar system with robotic probes. Every command sent to a spacecraft experiences a delay equal to the light travel time to that spacecraft. The Mars rovers, for instance, operate under a communication delay of between 3 and 22 minutes, depending on where Mars and Earth are in their respective orbits. When Mars is at its closest approach to Earth, at a distance of about 55 million kilometers, light takes roughly 3 minutes to travel between the two planets. Commands sent from mission control on Earth take 3 minutes to reach the rover, and any response or telemetry data takes another 3 minutes to return. That's a 6-minute round trip. When Mars is on the opposite side of the Sun from Earth, at its farthest distance of about 400 million kilometers, that delay stretches to about 22 minutes each way, a 44-minute round trip. This means the Mars rovers cannot be driven in real time like remote-controlled cars on Earth. Instead, engineers must plan each day's activities carefully, send a sequence of commands to the rover, then wait for the rover to execute those commands and transmit back the results. If something goes wrong, if the rover encounters an unexpected obstacle or a system fails, the delay means that mission control can't respond immediately. The rover must be smart enough to handle problems on its own, to detect hazards and stop before damaging itself. The Perseverance rover, which landed on Mars in February 2021, includes sophisticated autonomous navigation software that allows it to analyze the terrain, identify obstacles, and plan safe routes without constant human supervision. This autonomy is necessary precisely because of the light-speed delay. Human reflexes and decision-making cannot operate across a gap measured in minutes. The rover must think for itself. Now imagine controlling a spacecraft near Jupiter, which orbits at a distance of about 780 million kilometers from the Sun. Light takes roughly 40 minutes to travel from Jupiter to Earth, meaning a round-trip communication delay of about 80 minutes. If you were trying to steer a spacecraft through Jupiter's radiation belts or position it for a close flyby of one of Jupiter's moons, you couldn't make real-time adjustments. Any maneuver would have to be programmed in advance and executed autonomously. By the time you saw the results, the critical moment would have passed over an hour ago. The Juno spacecraft, which has been orbiting Jupiter since 2016, performs close flybys of Jupiter's moons, sometimes passing within a few thousand kilometers of their surfaces at speeds of tens of thousands of kilometers per hour. These encounters are completely automated. The spacecraft follows pre-programmed instructions, adjusting its orientation and instruments without human intervention. Mission control watches the flyby unfold in delayed telemetry, seeing events that happened over an hour ago, unable to intervene if anything goes wrong. For the outer solar system, the delays become even more extreme. Saturn is about 1.4 billion kilometers from the Sun, giving a light travel time of about 80 minutes and a round-trip delay of 2 hours 40 minutes. Uranus, at roughly 2.9 billion kilometers, has a light travel time of about 2 hours 40 minutes and a round-trip delay of over 5 hours. Neptune, at about 4.5 billion kilometers, has a light travel time of about 4 hours and a round-trip delay of over 8 hours. When Voyager 2 flew past Neptune in August 1989, it was so far from Earth that radio signals took over 4 hours to reach the spacecraft. The entire Neptune encounter, the close approach to the planet and its moons, had to be choreographed and programmed months in advance. The spacecraft executed its encounter sequence autonomously, while mission controllers on Earth watched the data stream in, seeing images and measurements of events that had occurred 4 hours earlier, powerless to change anything if problems arose. Voyager 2 discovered geysers of liquid nitrogen erupting from Neptune's moon, Triton, photographed Neptune's great dark spot, and measured the planet's magnetic field and atmosphere. All of these discoveries were made by a spacecraft operating independently, 4 billion kilometers from its creators, executing commands written by people who wouldn't know if they had succeeded until hours after the fact. This is the reality of deep space exploration. The farther we send our robotic emissaries, the more independent they must become. The speed of light enforces a kind of cosmic loneliness on these machines. They travel to distant worlds, make observations and decisions, and experience things that we won't learn about until long after those moments have passed. By the time we see the first image from a new moon or planet, the spacecraft has already moved on, already experienced what we're just now witnessing. New Horizons, which flew past Pluto in July 2015, was about 4.7 billion kilometers from Earth during the encounter. Radio signals took 4 hours, 30 minutes to cross that distance. The entire flyby, including all the critical instrument sequences and trajectory corrections, happened autonomously. The spacecraft had a single chance to get everything right as it hurtled past Pluto, at over 14 kilometers per second. Mission Control could only wait and hope, watching data arrive from events that had occurred over 4 hours earlier. When the first high-resolution image of Pluto's heart-shaped Tombor Regio appeared on screens at Mission Control, the spacecraft had already photographed it, stored the data, and was racing away into the outer solar system. The image showed a world that New Horizons had left behind hours ago. The spacecraft was already experiencing new views, new perspectives on Pluto's far side, while we were still seeing its initial approach. This disconnect between experience and observation, this unavoidable delay imposed by light's finite speed, creates a strange relationship between humanity and its distant spacecraft. We build these robots, launch them on decade-long journeys, and then watch their adventures unfold in slow motion, always lagging behind their actual experiences by minutes, hours, or even days. The Parker Solar Probe, which is studying the Sun's outer atmosphere by diving repeatedly through the solar corona, experiences the opposite problem. At its closest approach to the Sun, it's only about 6 million kilometers from the solar surface, but still about 144 million kilometers from Earth on average. Light from the probe takes about 8 minutes to reach us, but the probe itself is moving so fast, over 190 kilometers per second at perihelion, that it traverses huge distances in that 8-minute delay. When Parker Solar Probe sends back data from its closest approach, it's describing conditions it experienced 8 minutes ago, but in those 8 minutes it has traveled over 90,000 kilometers farther from the Sun. The solar environment it's currently experiencing might be significantly different from what the telemetry is showing. Mission controllers must account for this lag when planning instrument sequences and maneuvers. Even our most advanced communication technologies cannot circumvent these delays. Laser communication systems, which NASA and other space agencies are developing to increase data transmission rates from spacecraft, still transmit information at the speed of light. They can send more data per second than radio transmissions, but they can't send it any faster across distance. A laser signal from Mars still takes 3 to 22 minutes to reach Earth, just like a radio signal. It arrives with more information encoded in it, but not any sooner. If you made this far, I am sure you will love this other video. At the left side of the screen, how long would it actually take us to reach Pluto or Proxima Centauri? Discover why interstellar travel requires multi-generational thinking and how weight equation paradoxes challenge mission planning. See you there.